All right, well, thanks everybody, and wish I could be there, but circumstances being what they are, I am talking to you from my lovely office here in Mobile, Alabama. I'm thrilled to kick off today's session, where we're going to be talking about innovation and designing for the future. And, oops, sorry, we are seeing presenter view. Let me swap. All right, is that better?
Much better. Thank you. Sorry.
All right. Technology is wonderful. All right, now we're good. So, specifically in my talk today, we're going to provide some general information about not only preparing for the future, but thinking about future sea level rise and storms specifically as they relate to living shorelines design. Now, I've kept the presentation fairly general. So you're not going to see any fancy equations or anything too technically overwhelming. So it'll be a nice, easy way to kick off the morning if you're not fully caffeinated yet. But just as a general overview of what we'll be talking about for the next few minutes, we'll start off with just overall living shoreline goals. So what is it that we're trying to accomplish with these projects? And sometimes it's helpful to understand what we're trying not to do or what we're not expecting to achieve as well. We'll then talk about future sea level rise and storms, what we expect might happen, and how those might impact performance and design in the long run. Then describe some performance considerations, provide a few key ideas or concepts for creating robust designs for your projects, and then kind of close with a few summary points of just kind of remembering the bigger picture that involved with living shorelines projects. So one thing to keep in mind, the thing I like to tell people when I'm talking about living shorelines, and all of you in the audience and online already know this, but there's a difference between a strategy and a solution. So fundamentally, a living shoreline approach is a concept or a tool or a strategy for managing our shorelines and protecting the intertidal zone. It's not a solution to the problem. So we're not addressing the background erosion problem, or we're not addressing the loss of habitat and the things that led to that loss of habitat. But we're trying to manage the provision of ecosystem services through the process of designing, creating these living shorelines projects. And so it's important to keep this in mind because it's also important in terms of setting realistic goals for your project. When we're talking about not solving shoreline erosion, but managing shoreline erosion through natural and or constructed elements that, again, preserve or enhance the habitat value provided across the intertidal and subtidal areas. In terms of future sea level rise and storms, we're going to have a lot of work ahead of us, and we're not exactly going to know where we're going to be in terms of a future sea level rise path, probably at least not for another 10 or 15, maybe even 20 years. And that's really where a lot of these science-based and planning-based scenarios start to really diverge in a significant fashion. But in the context of living shorelines, it's important to keep in mind that mean sea level is the fundamental geologic control of shoreline position worldwide. So you can't really hide from mean sea level, and that is going to dictate ultimately your shoreline position. And also the tidal datums that go about that mean sea level position are going to be important within the context of establishing where some of your habitat is going to be. Now, we do know that global sea levels are rising. We also know that local and regional processes are going to make that rate look a lot bigger in most parts of the country. There are certain exceptions, of course, but for the most part, we're going to be dealing with relative sea level rise rates in the future that are higher than what we've seen in the past. Now, there's significant uncertainty in pretty much all of these future scenarios. This graphic that I have on the slide right here is something that we created for a federal publication last year. And what it does is it shows in two separate figures a combination of science-based projections and uncertainties related to global mean sea level rise, and also the kind of the programmatic or planning-based scenarios that the NOAA Interagency Task Force released in 2017. And so the dashed lines show those incremental kind of arbitrarily spaced planning scenarios. But then the blue shaded areas show the science-based projections related to RCP scenarios 4, 5, 6, 0 and the lower portion, and then RCP 8.5 in the upper panel. The blue shading is basically the 90% uncertainty range. So it's the 5th and 95th percentile marks about the median value. And so we see that the science-based projections are, in most cases, kind of on the low to medium range of the planning scenarios. And that's important because while the planning scenarios, especially as you look at some of those extreme projections, they look very dire and obviously very concerning. Now, those are scientifically plausible outcomes, but certainly less likely than most of the other outcomes. And so when you look at these scenarios and you kind of head is swimming with how to make a decision, keep in mind that the science-based scenarios still kind of, predict with good certainty, for the most part, that our future sea level rise conditions are going to be kind of in the low to moderate range of these planning scenarios. Now, also related to future sea level rise, as mean sea level increases, all of your datums will also increase along with them. So your tidal datums, mean low water to mean high water, are going to shift along with that change in mean sea level. All of your storm datums. So everything that we use right now in the context of design related to still water elevations, whether it's flood-based design or whether it's ecosystem-based design, those storm datums are also going to change with future sea level rise, and sometimes in a nonlinear fashion. So just because you get 1 foot of sea level rise doesn't necessarily mean that the storm surge for some event is just going to be 1 foot higher than it would. It could be 3/4 of a foot higher in some places, and it could be 1.5 feet higher in other places. Things we don't often talk about, especially not as an engineer, are your biological and ecological datums. So the areas about the tide range where you find different sorts of habitats that are typically very important in the context of living shorelines design. So all of these things are going to creep up over time with future sea level rise. And it's also going to lead to more frequent and greater amounts of inundation. And so NASA, this is a graphic from a NASA flooding tool that is now online. It's relatively recent. And it's nice because you can pick tide gauges around the country and look at the projected number of flooding days per year based on different NOAA planning sea level rise projection scenarios. So we know that with an increase in flooding, some of our static infrastructure without adaptive capacity. So these are more of the engineered elements of our living shorelines designs, like breakwaters or sills, and even sometimes constructed reefs. If they don't innately or inherently have any kind of adaptive capacity to change over time, either with or without input, these things will become a lot less effective over time as the amount of inundation increases, both in terms of magnitude and frequency. And some ecological communities, whether it's marshes or mangroves or oysters, we know in the past have done, a fairly good job in certain cases of keeping pace with historic rates of sea level rise. But there is a limit to which in the future, as to the rates that they can continue to keep up with. In the case of marsh, in some cases, even, in spite of consistent delivery of sediment to the system, a recent publication showed that, that there are future sea level rise rates at which that marsh will be completely inundated and not be able to keep pace. We also know in terms of storm impacts in a changing climate that the overall, there's going to be an overall increase in the frequency of the lower return period events. So these are things with high exceedance probabilities, storms that occur very frequently. These are often the storms that impact our shorelines the most, because they are places where storms with relatively low water levels, but a lot of wave action that tend to drive a lot of erosion right at along the intertidal zone. These also tend to be the places where a lot of our ecological communities exist, like our marshes and our mangroves, and in many cases our oyster or different shellfish reefs. So they're exposed to tremendous forces during these frequent but lower intensity events. And that's problematic because this is the group of events overall in terms of storms that are expected to increase in frequency the most. They'll also somewhat increase in magnitude, but mainly increase in frequency will be a problem, especially for some of our design elements. Now, future sea level rise will lead to higher water levels and larger wave heights. And we know this because as the sea level rise goes up, there's less friction. Storm surge in many cases will have a nonlinear response to that increase in water level. And also the larger water depth can support a much larger wave height. Now, living shorelines functions need to address system reliability while the design is resilient to hazard risk. And what I mean is that if your design event, say, is a 10-year return period event, so for example, you've got something with a 10% exceedance probability, there's only a 10% chance that storm would exist during that year, but there's a 90% chance that it wouldn't. So your living shoreline design really needs to focus on the 90% chance that the storm isn't there, because that's the greater amount of time in which it needs to provide those ecosystem services. But think in terms of how sea level rise will change our risk over time, and also climate change impacts like increasing storminess. We're going to see, essentially, because sea levels are rising over the life of a project, and because the storm profile may change over the life of a project, we're going to have changing risk. And so consider this example where in the present day, we have, say, a 25-year return period event that might serve as a design basis for a project. Then that's got a 4% annual exceedance probability. And for a 20-year design life project, that's about a 56% chance of risk of seeing that event or seeing something larger than an event. But say under a future sea level rise scenario A, that same event could occur much more frequently and be a 10-year return period event with a 10% annual exceedance probability and an 88% risk over that same period of time, versus a higher future rate of sea level rise where that now becomes a 5-year return period event with a 20% annual exceedance probability and a 99% risk of occurrence or exceedance during that 20-year design life. So sometimes it's helpful to think about, once you've identified a sea level rise scenario of importance, kind of start at the end of your project and work back to the beginning and think about how that risk is going to change over time. Now, in terms of performance considerations, if we were to essentially make a plot of performance versus structure submergence to look at what might happen over time with increasing sea levels for components that have no natural adaptive capacity, say like a breakwater or a sill, over time, that structure is going to come inundated more often and by greater amounts. So the habitat value really is going to increase over time. But your wave attenuating capabilities to stabilize the shoreline and kind of, or at least promote shoreline stabilization and reduce erosion are going to decrease as that structure becomes submerged. And so you're going to have this trade-off, and it really kind of becomes an optimization problem where's the balance point of the sweet spot where we can optimize this balance between providing good habitat in our structure, but also providing the wave attenuating capabilities that we need to address the forcings of interest. Other potential challenges that we don't often think about, what are going to be the changes in the physical processes. So sea level rise leads to, larger wave heights, because now if the water depth is going up, generally wave heights scale as water depth to the 3/4 power, and erosion is proportional to wave energy and power, which is a function of the wave height squared. Then what will happen is, with time, as sea level rise goes up, our wave heights will increase because of the large water depth. Our erosion potential increases in a nonlinear fashion. So as an example, 1 meter of future sea level rise could increase your erosion potential by a factor of 3 over the life of a project. And that's a fairly substantial increase. Well, what about our ecological systems? So consider this wave tolerance plot for Spartina alterniflora from Rowland and Douglas in 2005, where the dark solid line there is basically the division between no Spartina and Spartina along a shoreline, where your vertical axis is significant wave height and the horizontal axis is frequency of occurrence. Say you might start off with this cyan curve here, which is present day scenario, but with sea level rise, you might see the frequency of occurrence either at the low end or the high end start to increase, because for two reasons. Number one, our wave heights are larger because of sea level rise, but also the increase in storminess is going to drive these wave events that occur more often. Now, in terms of creating robust designs, we need to select and apply an appropriate design strategy. And this could be the difference between taking a top-down or a bottom-up approach. And by that, I mean, in a top-down approach, we identify a specific elevation at which we know there's going to be a tipping point or a problem. And we kind of look at the range of timelines over which that tipping point may be reached. And we design to accommodate those impacts. Versus a bottom-up approach where we say, if we've got, say, a 20-year life of a project, we're going to look out to 2040 for our relative sea level rise curves, and then we're going to identify the range of elevations that we might need to accommodate over time. And then think about how the risk and uncertainty is going to change over the life of the project associated with those decisions. And think about the inherent adaptive capacity of your system, whether it's a natural system or a built system. So for this example, think of this trapezoidal structure as a breakwater or a sill, where over time you start here, but sea level rise increases, and now you've lost your wave attenuating capability. So you might just alternatively come back and add more stone to the top. And that's great, but the issue here is that now we've kind of flipped those two curves, because as we start to build the structure higher, it's great for wave attenuation, but at some point you receive diminishing returns on habitat. So for natural systems, it's important to provide some accommodation space for migration and adjustment to sea level rise, and think about spreading your project out over the intertidal zone and maximize your benefits, and trying to identify or avoid scenarios that may lead to drowning in place, either of shellfish reefs or vegetative communities. And as I said earlier, with the top-down approach to design, think about tipping points in the functional design. So are there a certain elevation at which this just fundamentally won't work because a nearby project site or a structural element, a feature, whether it's a road, a seawall, or a homeowner or a client might decide, hey, I need to do something else. So in terms of the bigger picture, as we close out here and move on to the next speaker, we've got three things. The points are choose wisely, set realistic goals, and then finally the bottom line. And choose wisely. Storms are fleeting, but sea level rise is forever. And what I mean is that the storms come and go, but sea level rise is a permanent static boundary condition that we can't avoid over time. In terms of setting realistic goals, you can't stop sea level rise and they won't prevent storm damage. So keep that in mind as you are designing your project and setting realistic goals for its success. And then finally, keep in mind that living shorelines are a management strategy, not necessarily a solution to all the problems.